Hello, everyone. Thanks for joining in with us today. Welcome to today's topic, Cracking the Code, Essential Testing Tactics for High Voltage Circuit Breakers. My name is Michael Fleischer, and I'm the Americas Marketing Communications Manager for Megger. I'll be acting as the moderator for today's presentation and acting as the support team for any technical issues or questions you have with our presenter team. Speaking of questions, on the left side of your screen, you'll see an Ask a Question window. You can submit questions at any time during the presentation, and I will read those questions out during the Q&A segment at the end of our webinar. Additionally, your certificate of attendance, a copy of this presentation, and a link to the recording of this webinar will be available to all attendees in 2 business days via the email you used to register. So our presenter today is Brett Kersey, Applications Engineer. To assist with that question and answer session, we also have joining us Joseph Aguirre, our Principal Engineer here at Megger, and Jason Christ, Applications Engineer. With that, I'll throw things over to Brett. Thanks so much for joining in today, Brett.
Absolutely, glad to be here. All right, so like you said, my name is Brett Kersey. I'm an application engineer with Megger. Today, we're just going to be talking a little bit about testing high voltage circuit breakers, different techniques that you can go about. We're going to talk about the conventional timing, and then we're going to go into a few other techniques that can be used outside of conventional timing. So just give a little understanding. Some people are new to this, some people are senior. So circuit breakers are some of the most important components that we have in our modern electrical power system. Circuit breakers' point of job is to, within extreme tolerances, open up and distribute any detected faults on the network, or for safety reasons. These are costly components that it's protecting, such as a transformer. So that sometimes they operate after months or even years of inactivity. So we ensure proper functioning and itemization of the network reliability with efficient testing. So moving on. On today's agenda, we're going to talk a little bit about basic circuit breaker types and the components of those breakers. We're going to go over some time and travel analysis, and then we're going to touch on a few other specialty testing that you can do, such as dual grounding, dynamic resistive measurements versus static resistive measurements, post-trip, and then we'll finish it up with a little conclusion, and then we'll do our Q&A. So as I said, we're going to start it off with just going over some basic circuit breaker types and components. So to start off this conversation, we're going to talk about the differences between a live tank and dead tank circuit breaker. So simplicity's sake, dead tank is a tank that is grounded in service, has more insulating medium in it, such as oil, air, or gas. The CT is all mounted on the bushings itself, and it's most common in the US. And then with a live tank, the tank is live on the line voltage. It has less insulating medium, oil or gas, and it requires standalone CTs per tower. These are primarily used in European markets. However, they are growing slowly in the US market. So just to go over that again, dead tank, if you look right there, I highlighted the tank. That entire casing is grounded. So all the interrupter, all the linkage, everything inside that tank is around a grounded sphere. There is no live voltage. And theoretically, I'm not telling people to do this. If you walked up to it in a live substation, you could touch the outside of that casing and you would be fine because it is grounded. Now, again, I would not recommend doing that. When we talk about live tanks, as I said, the tank is live. So if you look up there on my little red dot, the interrupter inside of an insulation medium, that is a live outside on that tank. It is not grounded. So that is just the basic understanding of what a live tank, dead tank is. Now, when it comes to different circuit breaker types, when it comes to live tank, dead tank, you have different breakers with different mediums for insulation material. So for live tanks, you can have vacuum breakers, so high voltage, minimum oil. So if you remember on the last slide, which red right there, that's going to be filled with either SF6 or oil. And if you look at the dead tank, obviously that's a lot more room for that medium. So you can also have air blast live tanks and FS6 live tanks, either circuit breakers or circuit switchers. When it comes to dead tanks, you can again have vacuum. These are generally medium voltage, 15 kV distribution breakers. You can have bulk oil. Bulk oil breakers are not as common as they used to be. I believe they stopped manufacturing them back in like the 1960s. There are still some out there in service. Retrofitting or replacing parts on those isn't a big deal. The parts are still pretty available on the market. And again, you can have FS6 breakers, be that a circuit breaker or gas insulated switches, switch gear. So now that we've talked about the difference between live tank and dead tank, let's talk about the operating mechanisms. So you have two different types of operating mechanisms. You have a gang operated and an independent pole operated or IPO operating mechanisms. So gang operated, this means that the switch can be operated simultaneously by a single mechanism. And gang operated ensures that all poles of the switch open or close together, in which is important for safety and coordination of the electrical system. When it comes to IPOs, independent pole operated, one mechanism per individual phase. It's generally above 245 kV. However, for voltages below 245, you could use these in special applications such as synchronous switching or higher amperage ratings. You can also be used to trip in recos on only one phase if there is a single phase fault. So now we talk about live tank, neg tank, the operating mechanisms. Let's talk about breaks per phase. So breaks per phase or interrupters are used to divide the stress during opening or closing operations on the main contacts or the secondary contacts, also known as arcing contacts. We'll talk a little bit more about that when we get into dynamic resistance measurements. So the number of breaks per phase can go from 1 to 16 depending on if it's a live tank or dead tank. As the voltage increase, generally the number of breaks increase, like I said, to help clear off that stress during opening or closing. If the circuit breaker does have resistors, there can be one resistor per one main contact. So one break, one resistor. So you can have 4 breaks and you have 4 resistors on each break, 1 resistor on each break. So dead tank circuit breakers, as far as testing dead tank circuit breakers, from a field perspective, it's only 1 break in the entire unit. It could have multiple breaks inside the casing, but if you remember, for a dead tank, all that linkage is inside that grounded case. So from perspective of testing, it's 1 internal break. So SS6 dead break circuit breakers are 1 or 4 internally. Bulk circuit breakers can have as many breaks internally as the manufacturer sets up. And then live tank circuit breakers are generally can have 1 to 16 per phase. Got a few examples here. So this is a 1 break per phase dead tank and 1 break per phase live tank. So this is an example of 2. I'm not sure if y'all can see my mouse or not, but you have 1 break here and then another break here. That's on a dead tank. Also, that's on a live tank. And this is the dead tank. If you look right here, you'll see a linkage between these 2 towers. So you have your 1 break there, 2nd, 3rd, and 4th. All right, so you heard me talk about interrupters earlier. That's what's inside of the breaks per phase. The interrupter is just, it's meant to extinguish the arc while doing an open or closing command. The main contact in the circuit breaker is the current carrying element between the stationary and the moving part of the interrupter. And then depending on the classification you have, so this is a interrupter for a vacuum breaker over to the left. Generally for a vacuum breaker, you don't have that arcing contact, just the main contact. And then you also have an FS6 when you have breaks per phases, you do have, that's on the right, it has a primary contact and a secondary contact. So like I said before, the primary contact is the main current element carrying, that carries the current, and the arcing contact is just there to help extinguish the arc, either doing a close command or opening command. So another part of this that you can have on your breakers, you can have capacitors. There's 2 different types of capacitors. You have your grading capacitor and your shunt capacitor. So a grading capacitor are sometimes used on a circuit breaker with 2 or more interrupters in series. That way you can attain a uniform distribution of the voltage stress across the open gaps. The gradient compressor is connected in parallel with each interrupter unit and has a standard value for its ranges in a few nanofarads capacitor. The shunt capacitors are used to increase the short circuit capabilities of your circuit breaker. In addition to capacitance increase, the time delay for the initial transient for recovery, and has therefore an impact on mainly on the short line fault performance. You heard me talk about it earlier. You can have resistors with your interrupters. So there are two types of resistors. You have your pre-insertion resistor and your post-insertion resistor. The pre-insertion resistor contacts are mainly used for higher voltages, 362 kV and above. The main purpose of the pre-resistor contacts is to limit the transients on the network when you're reconnecting the line with no load. They are only used during closing and are connected in parallel with the main contact. The pre-resistor connection closes about 8 to 12 milliseconds before the main contact, and the resistor provides that inrush limiting by the momentary insertion of the resistive device into the circuit before fully energizing. And then as far as the post-insertion resistor goes, or also known as a dampener resistor, they're just used to dampen the restrike voltage when you can appear during opening operations. They are mainly used on older circuit breakers, such as air blasters, but not as common as they once were in today's market. So now that we've talked about some of the basic understanding and components of high voltage circuit breakers, we're going to talk a little bit about timing and travel analysis. So what is timing and travel analysis? So timing refers to the time in seconds, usually milliseconds, from the moment that the circuit breaker receives that pulse signal to either open or close from the protective relay or from the command from the unit itself. To time that operation is complete when the contacts reach their final resting place. This can also refer to a specific point in time or specific period within the operation. And the main factor is that the time measurement is relative to time zero. There is no speed measurement. If there is any resistors contacts, either pre or post in line, the timing is still measured the same way, and it does include the measurement for the resistance of those resistors. As far as travel analysis goes, of the breaker mechanism through either analog or digital channels, it just depends on what type of a breaker analyzer unit you have. Some of them are digital, some of them are analog, some of them have both. With the usage of a corresponding transducer mechanism attached to a specific point on that circuit breaker, the analog or digital signals are measured for the entirety of the operating period by the transducer and then converted to a travel parameters, either that be length, angle, or speed, just depends on what type of transducer you have. And we'll get more into the different types of transducers here in a little bit. So, and you may have to use manufacturer conversion tables, depending on if you have a rotary or linear transducer. Again, we'll talk about that a little bit later. And the results will display numerically and graphically to show the behavior of the mechanism throughout the entire trial. So before we start getting into the testing, let's talk about how to do your hookup with your test set. It doesn't really matter if it's a Mega brand. It doesn't matter which brand it is. Generally speaking, these connections are pretty much the same. So you start off with your control circuit. This is what's going to actually give the command to the breaker from your test set to either open or close based off the closed coil and open coil or trip coil. So once you have those connected, the next thing you're going to want to connect will be your terminal leads. This is what's going to sense when those breakers come open and close based off the continuity check of those instruments. So put a small voltage on one of the leads, and once that voltage allowed or current is allowed to continue back to the test set, it stops the time. You also have, if you are using a transducer, you have your travel mechanism cable. Again, like I said, this can be analog or digital, depending on your test set. It could have both, it could be one or the other. And then obviously, you always have your ground. So getting more into that, as I said, the first connection is going to be your control circuit. So you have your terminal access points, and you should have a drawing for that medium voltage control power circuit. So the first thing you're going to hook up will be your power supply. Based off this drawing, it's going to be on node 1 and 2, as I have selected there. Then you're going to do your closed coil. In this case, it's node 7, in line with your closed circuit. And then you're going to do your trip coil or open coil, and that's going to go to node 9. That's in line with the trip circuit. Now, as you heard me mention earlier, there are all different transducers out there. There's linear and rotary. So the contract travel motion is captured by connecting a travel transducer to the moving parts of the breaker's operating mechanism. This transducer can provide analog voltage relative to the movement of the contact. The motion is then presented as a curve, as I said, where distance and time allows for further analysis. So they're all two different types. As I said, there's a linear and rotary. So linear, I got a little picture here on my bulk oil circuit breaker. It's directly in line with the operating mechanism. Obviously, the type used depends on your circuit breaker. Most of the breakers allow for either one to be used. However, do follow the manufacturer's recommendations. But once you select a certain type, you should stick with that for any subsequent testing that you do. That way you can trend your data over time. So if you use a linear and then you go out and use a rotary next time, those two values, you can see some comparisons, but they're not apple to apples. It's more apple to oranges. Then we have a rotary type. So the rotary type outputs a value in angle, so in degrees, typically in degrees. This is where those conversion tables may come into play. This depends on the manufacturer if they gave it to you in both linear or in degrees. The travel radius, it outputs a value in length and typically meters or inches. And as I said, the conversion tables are generally usually needed for that, for the rotary style. So when we talk about contact timing tolerances, we have different tolerances. So usually for the close and open time, you can reference the user manual for the circuit breaker. In light of not having that user manual or manufacturer data, there are all standards out there that do put forth, like IEC 62271-100, that says for breaker sensitivity, so phase to phase, all phases should close within 1/4 cycle of each other, and all phases should open within 1/6 of the cycle of each other. And then if you have any interrupters within the phase, they should be within 1/8 of the opening operation. You can also do, based off this timing, you can correct the timing between your main and your resistor contacts for pre-insertion. You can also do timing on your auxiliary contacts for your lead and lag time. So the resistor contacts can be pre and post insertion. Timing the resistor contacts are made simultaneously with the main contact, so there's no added test there. But the resistor contacts are only detected while the main contact is open. The resistor value is a good parameter for evaluation based off what the resistance of that pre-insertion or post-insertion resistor should be. As far as the auxiliary contacts go, there are no general time limits for the time relations between the main and the auxiliary contacts, but there is still important information to be seen now and understand based off your incoming signals to your auxiliary contacts. So we're doing our timing test. There are 5 main sequences that you can do. Majority of people only end up doing 3 of them. The other 2 are more situational based off how your protection relay is set up to work. So the 3 main ones are your close, your open, and your close open. So obviously the close measurement is the time elapsed between energization, getting that signal to close to the closed coil, and then the contact actually making contact. And then your open command is going to be the exact opposite. About when your signal gets to your trip coil, Your test step will start your timer. And once those contacts are fully open and no longer in stationary, it will stop the contact. It will, once the signal gets to your trip coil and the arc is extinguished, that is when the timing stops on that. And then you have your close open, which is also known as a trip free. It just simulates the breaker closing in on a fault to demonstrate that the breaker is free to trip whenever the close signal is still on. So basically the contacts will close momentarily. The mechanical close needs to be completed to be able to open. And as I mentioned, there's two other ones. You got your close open and your open close. These are generally for if you have a recloser operation for your breaker set up inside your relays, you can verify that they are operating as intended. So the contact state determined by resistive measurements in comparison against a threshold for typical timing test. We're going to go over another method called DCM, which is a dynamic capacitive measurement, which can be used with dual grounding, which we'll also talk a little bit about in a little bit. So for travel and motion measurements, you can get a lot of information from your travel trace or code that you're given. Any high voltage breaker is designed to interrupt the short current in a controlled manner. This puts great demand on the mechanical performance of all the components inside your high voltage circuit breaker, components such as the interrupting chamber, as well as the operating mechanism. It has to operate in specific speed to build up adequate pressure to allow for the cooling system, such as the air, the FS6, or the oil, to extinguish that arc that generated after contacts are separated until that next zero crossing. So here's a few examples. So for your close open speed, if it's too slow, it could be a problematic extinguishing that arc. The longer that arc persists, the more your contacts are going to get burnt up, which is going to require you to do replacements. If it's too fast, you could end up damaging the mechanical structure of your operating mechanism. And then you have stuff like dampening dynamics. So if you lack any dampening, you can have overtravel, which was mechanical damage again. If it's excess dampening or slow speed in the arcing zone, no extinction of that arc, like I said, and that could lead to more further and faster breakdown of your contacts. And then obviously rebound is one of the most serious of the problems you can have. A risk that you reignite that arc by the contacts coming back close enough to bridge that gap, and the arc comes back on. And in extreme circumstances, that can lead to breaker exploding. So travel and motion measurements are very good. Most people, from my experience, especially customers, they just want to see the timing analysis. And I do have a case study we're going to look over in just a little bit that points out the reason why doing the motion or the travel analysis is a very big benefit and should be done when you're doing timing. So we have our travel curve here. I'm just going to go through a few little points on it to show you what you're looking at on that trace. So the first thing you have is your stroke. That's the total distance of your operating mechanism traveled. Then you have your penetration, which is your contact penetration. This is the length measured from the initial contact touching to the final resting position of the operation. So this is referring to an interrupter with a main contact and an arcing contact. I'm going to go through the characteristics of that in a little bit and show you exactly what those are. Then you have your over travel, which is measured directly from the travel curve, and it's the maximum displacement beyond the resting point of the contacts during its operation. You have a rebound. As you can see, we had a little over. If you go back, we had a little over travel there. And because of that, it rebounded back up inside that dampening zone. So it is measured from the minimum displacement after the maximum displacement over travel to a final resting place. So basically, it's just vibration after that over travel. It overcompensates. It rebounds up past the steady state and then comes back down to steady state. And then you have your velocity or your speed. Your velocity, this can be calculated using speed correction points. Speed I lost my load, calculation points. The most common reason used for these speed calculation points is your arcing zone, as noted here. Is when it interrupts, it clears the fault. So it's to the point where the main contact leaves and that arcing contact leaves. So at the point of that main contact leaving versus the point of that arcing contact by having full separation in the arc extinguishing itself. So it's in the arcing zone. So at the point where the arc starts and the arc ends, you can figure out the velocity of your mechanism. So here's a few different little traces from all 5 operations that I discussed about. This is a example of a close operation. If you look here on the black line, that is your travel. And if you look, there's little black dots on each one. Those are your speed calculation points. Your red, your blue, white, your blue, yellow, and red are your timing code, your timings. The thin line is an open, and the close line, the thick line is your close. Is an representation of open. As you can see, the travel curve is going in the opposite direction. You have thick lines for close, and then it comes to your opening operation. This is the close open operation. As you can see, it goes open, it closes, and then reopens. And the same thing with an open close and the open close open. These are just examples. I'm not going to go too much into them. I just wanted you all to see what these traces look like. These are representations of good traces. So I mentioned earlier that we had a case study. So in this specific instance, circuit breaker was timed, and all the times fell within the manufacturer specs. They figured out, hey, we missed it. We should have done motion on it. They came back and did motion on it. And when they did, they noticed that B phase, which is yellow right now, and if we zoom in a little bit, had a good bit of oval travel inside of on the trace. If you look, the red and blue, which is A and C, they basically stayed uniform with each other all the way through the travel curve. But B was drastically had an oval travel, as well as the speed for B was 9.3 milliseconds versus the speed of A was 6.8. It might not sound a lot, but when we're talking milliseconds, that's a big gap. So what they ended up doing, they figured out it was a bad dash pot on B phase. They had to open it up to verify that. They replaced it, reran the test. And as you can see, B fell in line with A and C, and our speed came closer to each other. So what's the point of this story? All 3 phases were timed and fell within speculation. If they would not have done motion analysis on that breaker, B phase would have failed. It would have been a matter of time before that linkage broke, either in the next operation or the next couple. So the moral of the story is don't neglect doing motion on your breakers. Yes, hooking up the transducer to your breaker can be a headache at times, depending on what type of breaker you have. You also need to plan ahead. So once you figure out, hey, we need to test this breaker, you need to look up the model, find the manufacturer specs for what transducer you should use so that you're already ready before you up. It adds more time to your test, but as we just saw, just because the timing comes in correctly does not mean that you don't have oval travel or rebound on your traveling mechanisms, and you won't catch that unless you do a motion or travel analysis. So now that we've talked about the conventional way of doing timing in travel, we're going to talk a little bit about dual grounding and what the benefit of that is. So you asked, Brett, what is dual grounding? So in most times when you go to test a circuit breaker, you're already putting 2 grounds on. Most places require you to have a physical open disconnect and then 2 grounds and then work between those 2 grounds. However, when you go to do conventional timing, you have to lift one of those grounds in order to do the timing, because you have to put a voltage on one of your test leads. And if it's still grounded, obviously it's just going to go to ground. So once you lift that grounded connection, now you're making it, your test set is going to be induced with the capacitive couple current coming off any phases that are close to it and inducing onto your line. And if you don't have 2 grounds there, your test set is now that path to ground based off your instrument's ground lead. So dual grounding allows you to be able to have both grounds attached at at the same time and do your timing test. Now, like I said, traditional testing requires you to lift one side or both to perform the test. There's an increased risk to the workers, and it increases your time. So every time, especially for utilities, if you have to talk to operations, every time you have to lift to ground and unground, you have to talk to operations. There might be a delay in that and can add time to your testing. In some applications, it's difficult or impossible to have only one end grounded. But with dual ground, timing allows you to leave on both sides of your grounds and perform the measurement, making it safer and faster. So there's two methods that you can use for dual grounding. There's dynamic resistive measurements, which is DRM, or dynamic capacitive measurements, which is DCM. We're going to talk about both. We're going to talk about DCM first. It's the better of the two options. You do get a timing. You can do timing with DRM. However, it's going to be a resistive timing, and there's a lot of interpretation because you have to base it off the ground loop and the resistance of your contacts. So here's a little demonstration again. As you can see, with on the left, with one side grounded, you do have that capacitive current going through your test set, which is a risk for fault or damage to your test set. And then when you have both on, you're in a nice, clean, safe zone to work in. So dual grounding with DCM, dynamic capacitive measurement. So this technology makes contact timing possible with both sides grounded. It was also in no way different than conventional contact timing. You will not see a difference. It also makes it possible to test circuit breakers where removal of the jumpers or bus bar connections is difficult or time consuming, such as GSCI, CIS applications. So they have individual grounds that are hardwired in. You'd have to lift those and it's time consuming. With DCM, you don't have to lift those grounds. Also generator breakers, if you've ever tested a generator breaker, they're usually hard bust in there and it's very tight conditions. Everything has to be torqued. So the testing could take you a day, but the disconnecting and reconnecting can take you 2 days. And then obviously it works with all diagnostic tests for circuit breakers. So dynamic capacitance measurement, which relies on the natural capacitance of your test set, of your circuit breaker to distinguish between open and closed state. A simple representation of the circuit breaker consists of your moving contact, which is right here, and then your stationary contact that are separated by some type of medium, be that oil or SF6 gas. Generally, in a general sense, i.e. that circuit breaker is a capacitor. So as C being your capacitance, E being your dielectric in this formula right here, and A is the area of the surface or your breaker's contacts, and D is the distance between the two. When D decreases, so your distance between the two contacts decreases as in a closing operation, the contacts move from open towards closed, and C increases, so your capacitance increases. So once the breaker is closed, there's absolutely no capacitance. So how does this work? So this DCM is an attachment that can go with your circuit breaker analyzer test set. It uses a high frequency to retrieve a resonance on inside your breaker, either for your closed or open detection. Relies on the fact that the resonance frequency varies when the circuit breaker changes state. DCM is completely insensitive to 50 and 60 hertz. So if you are doing testing in a live substation, that interference will not be a thing for the DCM. Another way to think about this is if your test set is closing, you will have a very low current flow, where if the test set is open, you're going to have a lot of current flow when it comes to this variable frequency for dynamic capacitance testing. So dual grounding, timing, and DC. So we've already talked about how dual grounding is safer and faster for testing. It allows you to work on switchgear such as GIS, and your dynamic capacitance measurement is a simple hookup. It can be used with most types of circuit breakers or circuit switchers, but it is an accessory that you need with your breaker analyzer test set. And then it was also exactly like the traditional timing results. So moving on to dynamic resistive measurements in static resistive measurements. So we're going to start off with static resistive measurements. Most people know what this is. It's also known as another name as contact resistance. So this detects, and it's generally used on vacuum bottle circuit breakers, so high voltage vacuum breakers or medium voltage vacuum breakers. It detects any erosion on the contacts, any contaminants, loose internal connections, or low contact pressure. So the test with the breaker closed applies DC current and then measures the voltage drop across that, and then using Ohm's law, it can calculate the resistance of the circuit. So the value of the main contact resistance reflects the condition of the overall conducting parts. I would like to point out, if you do this on like an FS6 breaker that has the main contact and an arcing contact, that you are only going to get the resistance of the main of the whole body itself. In order to figure out the resistance of your arcing contact, you have to do the RM test, which we're about to talk about in a second. One point I want to add to this, international and national standards set forth a guideline for the static resistant measurement or contact resistance to eliminate any risk of attaining crazy high values for your tests, because for your results, because your test current is too low. Standards like IEC 56 states that the type of resistance is to be measured using a minimum of 50 amps, and not to exceed the breaker's nominal current. And then ANSI, ANSI, specifies that you should use 100, minimum of 100 amps. So just based off where you're located, just make sure that you're using a high enough value so that you're not getting anonymous results that are high value just because you're not using enough current. So that was contact resistance. There's not much to it. It's just putting current on the circuit with the breaker closed, and it monitors the voltage drop and then calculates your resistance. Now, dynamic resistive measurements. So this test concluded by injecting a DC current through the breaker main contact and measuring the voltage drop and the current while the breaker was in an operated state, so if it's opening or closing. The breaker analyzer, your circuit breaker test set, then calculates and plots the resistance as a function of time. If you do contact movement, so if you're using your transducer and it's recorded simultaneously, you can read the resistance at each contact point, and this method is used to diagnose the life of your arcing contact. So the DRM measurements, the arcing contact length can be estimated, and the only alternative to figuring out the length of your arcing contact, how much life it has left in it, would be to basically dismantle the circuit breaker and take a look for yourself and do a visual inspection. In the case of the FS6 breaker, the arcing contact is commonly made out of tungsten, and the contact slowly burns off and becomes shorter with each interruption of the load current. So every time you operate that breaker under load and there's an arc between the contacts, you're slowly diminishing the life of that arcing contact. The only way to figure out the length and measurement of that arcing contact is to do a dynamic resistor measurement, or to open up the breaker and take a look inside the interrupter. So why do DRM? Well, I just talked about it. It's an easy test. You can use it with dual grounding. It is a separate accessory that you can use with your circuit breaker analyzer. It does have timing built in, but you can do a timing curve on it. However, it's going to be a resistive curve. It's not going to be as easy to follow as your conventional timing or the dynamic capacity measurement it would be. So if you do normal timing, like I said, you're not going to get any information about the condition of your contacts, the length of the arcing contact. The arcing contact can get a load over high current inputs. So in order to do that, you're going to have to do DRM testing. So how does this work? It injects the current into the circuit breaker, and it measures the current and voltage drop as the circuit breaker operates, and then starts recording. So once that pulse signal gets to your open or your closed coil, it starts timer, and then it calculates the resistance, and then plots your current, your voltage, and your resistance versus time. And again, this can be done with dual grounding technique. It's as simple as Ohm's law. So here's a representation of how the interrupter works and what you're seeing inside what you would see inside your interrupter while you're doing an opening command. So your contacts are in a single state. If you look right here, the blue and the gray are your main contacts. The top portion of it is stationary. The bottom portion is your moving contacts. So your blue and gray right there, your main contacts, and this rod right here is your secondary contact, your ARCing contact. So you give the open command, the main contact separates. So all the current flow that was going through the main contact is now going through the ARCing contact. All this is meant to save your actual main contacts. And as it separates, that ARCing starts from the ARCing contact. As the moving contacts move down for FS6 or for oil, as it moves down in this tube right here, air or oil is forced up into it to help extinguish that arc from the ARCing contact. And obviously, once the arc is extinguished, the breaker comes to the open position. So when you're doing DRM, you're measuring this contact right here, your ARCing contact on your stationary contact. So here's a representation of what the DRM code looks like for an open. So obviously, you start your movement, you send the pulse signal to your trip coil, the contacts start moving. You get a small increase of resistance from the main contacts when it's sliding over the contact fingers. And then your main contact opens and the ARCing contact is conducting. Once the ARCing contact opens and the current drops and the resistance is infinite, you can then, based off these two spikes right here, so spike 1 where your main contact was opening and the ARCing contact took over, and then spike 2 is where your ARCing contact, the ARC was extinguished and you're in a safe state, the breaker was open and stationary. Your right line right here is your travel line. So based off these 2 points on the line where they intersect, the distance between these two is the measurement of your ARCing contact. That's how much ARCing contact you have left. The general rule of thumb is if you lose more than 6 millimeters of your ARCing contact, it needs to be replaced. So this a little overview of DRM. But to find out, the main purpose of it is to find out the condition of your ARCing contact and how much length you still have in that ARCing contact. It also will find any misalignment, any exhaust contaminants when the air or the oil is forced up into the ARCing chamber to help extinguish that arc, and any problems with your contact fingers on that main contact. Again, both sides of this can be grounded. You can do timing with this, but as I said, it won't look like conventional timing. It is more of a resistive curve that you would have to know the resistance of your ground loop and versus the resistance of your contact, and you have to put the threshold between those two. So it's not as straightforward as the traditional timing or the DCM, the dynamic capacitive measurement. So here's an example of a circuit breaker with a new contact. They did the DRM between the 2 points. They can calculate that the ARCing contact is 15.47 millimeters. They had a short circuit fault on the inside the breaker, and when they went back to retest it, they figured out that they only have 7 millimeters left of the ARCing contact. So they had to end up actually changing out that ARCing contact for a new one, and then we ran the test. So here's a picture of the ARCing contact, the stationary one inside the interrupter, as well as a good ARCing contact versus one that's been heavily corroded based off ARCing or short circuit faults. All right. Now that we've talked about all those, I want to talk about something called post trip. So like I said at the beginning, circuit breakers will generally sit idle in the closed position for months or even years without being operated. And in that time, the linkage, the grease, everything inside that operating mechanism becomes stiff and slow. So generally speaking, like I said, the problem is That first operation usually goes without any measurement parameters, so people don't usually monitor it. There is important information regarding the condition of your coil, your latching that is getting lost. So your solution is to do a first trip and to be able to determine the right moment to lubricate, replace your oils, and maintain the latching mechanism. So the first trip is a good and time-effective way to check the condition of your circuit breaker. It is used to document its behavior at its post-opening operation after it's been idle for a long time. So the measurement and the connections to the circuit breaker are carried out while it is in service, and all connections are made inside the control cabinet. So you're not going up to the paddles, you're not getting up to the overhead linkage, you're just going, everything's gonna be done inside the control cabinet. So the biggest benefit of using the first trip is it gives you a real world operation conditions. So what's it gonna look like when if there is a fault and that breaker has to open? So like I said, if it hasn't been operated in years, the first test will reveal if the circuit breaker is slow due to the problems in the mechanism or the coil amperage, or there's any corrosion or dry grease within your linkage. With the traditional method carried out, you usually you already have the breaker open, and then they might have operated it a couple times. So all that sore spots, that dry grease is already knocked off, and the breaker is back to operating within specs. However, that post-operation might not have fell inside specs, and that's the one that's most important, because that's the one that's going to happen if there is a fault on your line and that breaker has to open. If it's outside of that tolerance of speed, how fast it needs to operate, you may have a catastrophic failure inside your circuit breaker, and normal testing does not catch that, just the post-trip test does. You can also do a post-close test if the breaker has been left open in an open state for a long time and you're trying to close it into a live line. You can also do a post-close test as well. So how does it work? What are the connections? So the trigger is from the control house, obviously from the trip command, because you got to remember this breaker is still live, so you don't want to be there in front of the breaker operating it if there is a malfunction in the operating mechanism on its first trip. The control voltage is measured. The coil current is also measured via an external CT, and you can also do line current measurements via CTs clamps on the detection CTs that allow you to do timing. So when we're talking about just doing basic and we just want to verify the travel, how it operates via the tripping house. So if we want to control voltage measurement, coil measurement, and any auxiliary contact measurements. So what it is that you have a CT going up to your line voltage, which I have a little graph or something. And then you also want to measure your trigger time. So when that pulse from the command house gets to that node, it triggers the test set and starts its timer. Now, if you wanted to do timing, all you would need is 3 more CTs. They will go on the secondary line of your CT, on the CTs of the circuit breaker. So when the breaker is open, the current stops, the CT stop reading. Your secondary wiring will also will no longer have current on it, and your CTs will notice that, and it will stop the timer. So based off the pulse from the switch house, and then those secondary CTs no longer seeing current, it can time your breaker. Again, there's no need to go to the overhead level. All this is done from inside the control cabinet of your circuit breaker. And that pretty much wraps up for what we wanted to talk about today. So we're just going to do a little bit of conclusion here. So circuit breaker testing does require preparation. So information about your breaker. Does it have pre or post resistors? Does it have capacitors? How many breaks per phase? Is it a live tank, dead tank? What kind of apparatus is it? Is it oil, FS6? What kind of transducer does it take? Can it use both? Does the manufacturer recommend one specific one? And obviously, the test analyzer is simple, but it requires information from the manufacturer, like I said. So I like to think of it like this. Testing a transformer is easy. The connections are pretty much always going to be the same. The setup's always going to be the same. But reading the results of a transformer test does take time and knowledge of understanding what you're looking at. When it comes to circuit breaker testing, however, the data, the test results itself are easy to look at and interpret. But knowing you're going to hook up to your circuit breaker does take prior planning before you get out there. You neglect to do that proper planning, you're going to get out there and you're going to be twiddling your fingers for a little bit while you try to figure out what you need. Now, sometimes you don't have the opportunity to do some pre-planning before you go out the test. I understand that. But one big thing I do want to stress is that you should not neglect your travel analysis on high voltage circuit breakers. As we saw in that case study, they did just timing the first time. They did not see that B phase had that drastic over travel, and that breaker would have failed in service at some point. So we talked about post-trip, DRM, and dual grounding. Post-trip just adds a little more time to overall testing, but it is valuable information that's not lost. It can record information with little or no outage time because everything's done inside that control cabinet. You don't even have to, you can just, if you're still in service and you don't want to pull it out and you can base it all off your first trip test, that first trip test comes back good, you can push out the service for that maintenance service for that circuit breaker to a later date. And obviously DRM adds a little time as well, but it does give you more information about the interrupter of that circuit breaker, mostly the arcing contact. And then obviously we talked about dual grounding, how it's a safer and faster test. And if you use dynamic capacitance, it is the only method that works with DIS if you have gas insulated switches. Megger does offer a few products for circuit breaker analyzing test sets. Starting with our mid-range, we have an Eagle 200. It's relatively easy to use. It doesn't require much interaction from the customer. You can obviously put in all your information for your specs, your timing tolerances, and your travel tolerances. However, if you just want to get everything hooked up and go, you can put all that in on the backside. It does allow for dual grounding. You can do up to 4 breaks per phase, and it is DCM and DRM capable. On your higher range circuit breaker analyzers, you got your TM1700 series. It's a higher range circuit breaker analyzer, like I said. This is good for 2 breaks per phase. It does allow you to do post-trip, dual grounding, dynamic resistance measurements, and dynamic capacity measurements. And then our highest model would be the TM1800. This one is pretty much extremely configurable. On the top here, you have card slots, kind of like an old computer, where you can put in, say, your visual board. You can put in different contacts, so you can go up to 16 breaks per phase. Again, it can also do first trip, dual grounding, and dynamic resistant and capacitive measurements. All right, well, I thank everybody for their time. This is now time for questions. I'll turn it back over to Michael.
Thanks a lot, Brett. So as stated, we've wrapped up our presentation portion of our webinar here, and we're going to dive into the Q&A session in just a second. But I'd like to remind everyone that is about to head out that we'll have a copy of our presentation, a link to the recording of the webinar, a link to fill out a survey sent out over this weekend. If you'd like to fill that out, let us know how we did. We'd love to hear how we conduct these webinars, any potential topics we can tackle later this next year, and how we can improve upon this whole service that we're providing here. If you'd like to join us in person later this year to discuss innovations in the power transformer industry, we're holding our first Megger Power Grid Summit this year. If you'd like to learn more, there's a banner at the bottom of the screen. Additionally, if you'd like to view video recordings of previous webinars, as well as register for upcoming webinars, you can visit us on our website at megger.com/webinars. Additionally, we have our next webinar in this testing tactics circuit in September, titled DC DC breaker testing methodologies, assessment and performance testing. They'll be presented by Swapnil Marath. So we're going to jump into our Q&A segment real quick. Our first question we're going to send over to our panelist, Joseph Aguirre. So Joseph, how often do I need to perform timing and or travel of a HVCB?
So depending on whatever your maintenance protocol is, or if you follow IEEE or IEC. So most people only perform traveling measurements whenever they're doing like their 10 or 15 year PMs, right? So typically you should at least operate the breaker once every 2 years. So if you're just doing it to get a breaker operator signature every 2 years, and what that means is checking kind of how the coil and the motors or the actual current that's going through those to operate those, you should do that every about 2 years. That way you can make sure that the breaker is free moving, right? And it's not going to be slowed down over time. Other than that, it's usually up to your maintenance protocols, typically every about 7 years. Some utilities do this every 5 years. So whenever you're talking about just doing a measurement, right, as far as timing goes, you want to do that as far as the full gambit of testing as well every 5 to 7 years at minimum. If not, then just follow your regular PM, whatever your your company says, which is typically every PM cycle.
Thanks, Joe. As a quick reminder, if anyone has any other questions you'd like us to tackle during this part of the webinar, please feel free to write them in the Ask a Question window over there on the left-hand side. But going into our next question, we're going to throw that over to Jason Christ. Jason, is dual grounding testing recommended for a live tank and dead tank?
That's a good question, Michael. Live tank and dead tank testing should both be performed with the dual grounding method. It's a lot safer for the technician. So previous to the old way of testing with one side grounded and then one side having to be lifted, if you have nearby energized lines, you can get capacitive voltage. So it's recommended live and dead tank to use the dual grounded method. They both should get good results and be, they both should be safer for the personnel conducting the test. So, yes.
Thanks, Jason. Throwing things back over to Joe. Joe, I have a dual ground trip coil. Which do I test?
So I'm assuming you mean you have a dual trip coil, which means you have two trip coils on your trip circuit, right? So you should test both. So you'll have a trip 1 and trip 2. So whenever you're performing the open close and the trip free and the reclosing test, you should check all those with your trip coil 1, and then also run the full gambit of testing by utilizing your trip coil 2. So you'll have to take your trip coil 1 out of service. So that way you know that you're pulling from trip coil 2. Typically you have a trip coil 2 if you need that extra backup from that, or you have dual battery banks within like a larger switch yard. So you want to check both of those just to maintain and ensure that if one trip coil goes down, you're at least going to trip off your trip coil 2.
All right, thanks, Joe. Throwing things back over to Jason. What is a minimum voltage check?
So the minimum voltage check is the amount of voltage that the breaker is going to operate based on the control voltage for the coils. So like the close and trip coils run off of DC, usually on the UPS battery system out of the control house. And they have a range that may vary a little bit, but most of the time it's listed as between 70 and 140 volts DC. So your minimum voltage check is making sure what's the minimum voltage that breaker is still going to operate at.
Thanks, Jason. Throwing things over to Brett. What does it mean if I have a higher current on the closed coil when performing timing tests?
So increased current on your coil can come from a few different things. So it could be increased coil resistance. So if your coil has a higher resistance, it may draw more more current. If you have any mechanical instructions or binding, if there's any mechanical obstructions or increased friction within that coil, it could require more current to overcome that resistance. Any electrical shorts or insulation degradation can cause it, or if you have any power supply issues coming from the control house, or if you're supplying power to the breaker yourself. That can cause the closed coil to draw more current.
Thanks, Brett. Once more, going over to Joe. Can you please describe standard range of breaker test, e.g. contact resistance, contact timing, high pot, and IR?
Yeah, yes, I can. But before I do that, I'm going to add a little bit extra to what Brett was saying. A couple other things that could increase the current on there is usually like a gummed up breaker. So it's causing more current on that closed coil to actually come closed, because whether the operating mechanism itself is kind of gummy or the bearings are bad or something like that, you can get that increased current as well. So other than just the electrical side, it can be a mechanical feature binding or something kind of gummy on there, slowing down the actual motion, which is causing that current to rise. So back to the question of the different breaker tests. So the standard range, so contact resistance, a lot of people call that DLRO or a ductor test, right? So all you're doing is contact resistance, and depending on the standard of IEEE or IEC, you're going to use either 100 amps for contact resistance for IEEE or 50 amps for IEC. And that's just going to give you a low ohm value, usually in the micro ohms. And so depending on whatever your SOP is, or what standard you're abiding by, typically you'll go 50% from the highest reading. So if you had, let's say 100, 50, and 75, that 50 is within 50% of that 100, right? Or that 75 is 50% of that 100, so that's fine. But that 50%, right, or that 50 micro ohms might be a little bit too low, right? So the other two might be too high, so you might have to do some cleaning or more operating the breaker to get that contact resistance better. So whenever you talk about a high pot, typically a high pot test is if you have vacuum bottles on there, or you want to look at overall insulation integrity. So you're over potentialing it a little bit, and you want to see if anything's flashing over on that, and that's what you're going to use a high pot. You can also look at the milliamps with leakage current on there. As far as your IR test, that's your insulation resistance test, or what's commonly known as the Megger test. And all you're doing on that is and this is more people don't really utilize that test on your higher voltage breakers. That's usually on your lower voltage breakers. They typically do this, but it's still a fine test to do on your higher voltage EHV breakers, where you'll do your line to load, and you'll look at it with an open, right? And then you also look at your, while it's closed, your phase to phase, and then your phases to ground. And you want to make sure that there is a high ohmic value, usually in the gigs. As far as your contact timing, the contact timing is pretty much what this whole presentation was about. You want to make sure whenever you have that contact resistance and they're actually physically closed right here, how fast they separate. Because too slow, there will be an arc still in between them. And if it's too fast, you can have a restrike in between, where that separation happens so fast, the gas, or if it have a gas blast, gas puffer, or even if it goes through like arc chutes or anything like that, or a baffle where it kind of stretches out that arc, if it happens too slow or too fast, so there's a sweet spot in it, kind of like Goldilocks, where it's going to suffocate that arc to extinguish that arc. That way you have no power going through. So like I said before, if it's too slow, the arc could stay there and maintain. If it's too fast, you'll restrike back over as well.
All right, thanks, Joe. I'm going to throw this next question over to Brett, and I think we have two of them next to each other. I'm going to ask you this, the second one real quick. What equipment do you need to perform DCM testing with the TM1800? So
for the TM1800, the only thing you need is a separate device. It's called a DCM 1700. It goes in line with the TM1800, and that allows you to do that DCM test, that dynamic capacitive measurements test.
All right, thanks, Brett. And then I'll ask you the first question now. Are overtravel and penetration concepts shown in the plot on the earlier slides that we had run through the physical deformation, microscopic, of contacts, particularly when closing? How is that physically explained?
So the overtravel is a physical deformity in a way. So what it is, it's the linkage in that operating mechanism going past the point that it's supposed to. There's supposed to be a dash part in there. It's also known as a dampener. to help slow that down as it's making that into the closing connection. As far as the penetration concept, that is just simply the point of when the main contact versus when the arcing contact make connection. So the penetration concept isn't all that much of a physical decimation, but that over travel, you can get physical information from how much over travel it's happening. If you look back at that case study we talked about, that B phase had a high amount of over travel. What it was, it ended up being that dash part, that dampener, and was allowing that linkage room to travel further than it was supposed to.
All right, thanks, Brett. Throwing things over to Joe. During your when you were answering the question previous to the one Brett just ran through, when covering the breaker testing, do you recommend this test for a new installation? I think we might have lost Joe.
Yes.
There you go.
Yes. All right. So as far as new installation, yes. So this is a commissioning test, acceptance testing, right? You want to make sure that your breaker is going to operate how it's intended to operate. And this is the only way to check it, right? So you can also perform power factor testing on these higher voltage breakers as well with the contact resistance, installation resistance, and high pot testing if needed. Other than just the contact timing. So whenever you're asking, should you do this during commissioning? Absolutely during commissioning and during your regular maintenance intervals.
Thanks, Joe. I think we have this last question set over to you as well. And forgive me if I stumble over this. I'm trying to rework it as it's written out very well for a question to read, but not necessarily one to verbalize. So is it 50% of the highest or 50% of the lowest? Example, lowest value multiple by 1.5 times the lowest value equals the acceptable threshold for contact resistance.
Yes, so it depends on how you want to look at it. So it's usually the highest value, because the highest value is the easiest one to change. So whenever you're doing the multiplier, because if it's the lowest contact resistant, I'm getting all thumbs right now, or all tongues. So basically whatever you want to do, the delta in between the standard deviation between the highest and the lowest, they should be within 50% of each other. That's why I was saying the 100, 75, 50, that 50 is kind of low. So you want to get the only thing that you can do is get that, the 100 a little bit lower, right, to match it, because that means you'll have better contact resistance at that point. So what you have to do is just kind of actuate the breaker a little bit, or you might have to get some Scotch-Brite to clean it. So as long as that deviation between the two, so you can multiply the highest or the lowest by that 1.5, and then whatever that number is, which is 75, both of those numbers should be within that range, right? So you need to get either the 50 up or the 100 lower.
Thanks, Joe. We had another question come in. It's going to go over to Brett. Is there an acceptance criteria according to standards for circuit breaker timing tests regarding open and closing times?
Yes, there is. However, most times you're going off the manufacturer specs. So the manufacturer should specify the closing time and opening time and the tolerance for said time, and also for the travel. However, without light of those manufacturer specs, you can use standards such as IEC 62271 that states for phase-to-phase comparisons that the closed operation should be within 1/4 of each other cycles, and then the opening operation should be within 1/6 of the cycle. But 9 times out of 10, if you look at the manual, there should be specs on there. Some nameplates do also have the specs on there as well for the opening close and the close open time restrictions.
All right, thank you. Do we have that other question, or are we going to need to follow up with that, gang? So we have one question, and we'll try and answer the best we can. What is the double power test on the circuit breaker?
Okay,
I'll
when
send
you
it over
say
to Joe. Yeah.
when you say the double, I'm assuming you mean Doble. So Doble is just a power factor test, right? So you're just looking at watts loss or leakage current or capacitance, right? And so depending on who you talk to, some people don't find it. You don't get a lot of information on SF6 breakers. You get more information on your OCBs or your oil circuit breakers. So this is still a fine test to run. On those, you're usually run about 6 tests, all open tests, right? Back in my day when I first started, we had 9 tests, so you tested all 3 closed as well. So you're going to test this, and you're just going to get a power factor test, and it's going to be a relatively low power factor. Typically on SF6 breakers, mind you, it's going to be like the lower point 20s or sometimes point teens. So you're just looking at that insulation or the power factor value of your contacts in SF6 gas. And if you're looking at it with the oil, then that's where you get more information, and that's where you have that 0.5 values on there because it is submersion oil. And then you do have the cross arms, right? And then they kind of go up into the tulips whenever you're talking about OCB. So you get more valuable information with a power factor test that way.
All right, great. Thanks a lot. So I think we've actually knocked out all the questions we were asked here today. So we're going to conclude our Q&A segment here and indeed our webinar. But as a quick reminder before everyone disappears, we'll be sending out a copy of this presentation, your certificate of attendance, and a link to the video recording of this webinar over the weekend. If you'd like to review or register for any of our upcoming webinars, you can do so at megger.com/webinars. But I'd like to thank everyone in attendance here for spending some of your time with us on Friday. But after we conclude here, I'd appreciate if you could take a moment or two to answer our survey. That survey will also include a field for you to request a quote or a demo on any of the products we've had listed here today, as well as an area for you to let us know what you'd like us to cover in future webinars. But once again, I'd like to thank you all for attending, and I hope you'll have a great weekend. Thanks again.